Hello everybody. After today's minimum day lesson, in first period we reset this problem. We pretty much finished it. In third period I don't think we got as far as I would have liked and didn't really clearly delineate the steps and process that we should take on these so-called cliff problems. So I'm going to ask you to join me at my desk and let's take it from the top. Regardless of what period you're in, it might be a useful hopefully 4 or 5 minute video to watch, so let me see what we can do. A ball is thrown horizontally from a 55.2 meter cliff. That's the height of the cliff, how high it is. The cliff is overlooking the Pacific Ocean and it's thrown with a velocity of 5.5 meters per second. I want to stress that it is thrown horizontally with a velocity of 5.5. So that tells me that the horizontal velocity is 5.5. I'm going to make a sketch. The height of this cliff is 55.2 meters. That's a vertical distance. That's a vertical displacement. So on the trip down, the displacement is going to be negative 55.2 meters in the vertical direction. So let's call that y. We are no longer calling vertical displacements x, we're calling them y now. Furthermore, our ball is thrown horizontally, so the initial velocity, the 5.5, is entirely in the x direction. That's our vx. The ball falls, and at some distance from the cliff, it splashes into the water. So the cliff distance we would call our horizontal displacement, and we're now calling horizontal displacements x. I think our drawing, our sketch, is good. How long is the ball in the air for? Turns out that the only thing that determines the time of flight is the vertical distance that it is falling and the acceleration due to gravity. So because of this does not matter. In fact, if this was 10 times faster, it would just go 10 times farther, but it would take the same amount of time to fall because this height is how far it's really falling due to gravity. Again, the acceleration due to gravity is also important, but on Earth we always use 9.8. If we were on a different planet, it would be different, but on Earth we're going to use 9.8. So to determine how long the ball is in the air for, I'm going to make a vertical list. Initial vertical velocity, final vertical velocity, acceleration, time, and vertical displacement. Let's go ahead and fill in our list. We know the acceleration due to gravity is that of gravitational acceleration, 9.8, negative. And we want the time. And we know that the displacement on the way to the water is 55.2 in the negative direction, downward. The only thing, we need one more number. And what many students fail to realize is that the 5.5 meters per second is all horizontal. It wasn't thrown vertically at all. It was thrown perfectly horizontally. So the initial vertical velocity, just as if we dropped it, is 0 meters per second. That makes our final y velocity not applicable. And I'm going to go to my new equation 3. I think when we passed this out in class, it was yellow, but notice that equation 3 is the same as it always was, but now it's we've replaced x with y and v naught with v naught y, initial vertical velocity and vertical displacement. Nevertheless, it reads displacement in the vertical direction is equal to the initial y velocity times time plus 1/2 at squared. I'm going to write that equation down. Again, the initial vertical velocity is 0, and 0 times anything is still 0. So this whole term goes to 0. And this becomes y equals 1/2 at squared. If we do the algebra and solve this for time, we get t equals the square root of 2y over a. I'm going to plug in my values. 2 times 55.2 negative equals, divided by 9.8 negative equals 11.26. That's what's under the square root, so I take the square root of that, and I get 3.356. Rounding that off to, let's see, well, we had 3 sig figs here. We don't usually let gravity affect our sig figs, so I'm going to round this to 3, and I'm going to call that 3.36. You would not be penalized if you rounded this to 3.4. But again, the truly given value, the height of the cliff, was 3 sig figs, so I'm going to round it to 3 sig figs. How far from the base of the cliff does the ball splash into the ocean? Well, that's a horizontal thing. That's really x. That's what we're looking for. In the horizontal direction, we have 3 variables: horizontal displacement, horizontal velocity, and time. And time is really shared in the 2 dimensions. This time and this time are the same time. You'll often find with any problem that involves 2 dimensions that time is the key. Sometimes you use horizontal lists to find time and then go to the vertical. Sometimes you go to the vertical and find time and take that time to the horizontal and use it. Let's do this quickly. We know that the horizontal velocity was 5.5. So I'm going to put that in here for my Vx. And we know we want to find x. So the equation in a horizontal direction, there's only one equation. It's just v in the horizontal direction equals x over t. Because I want to find x, I'm going to solve for x. And when I do so, I multiply both sides by t, and I get distance equals horizontal velocity times time. Now all we have yet to do is just plug in our values. In this case, I did use a number that was given to me that had 2 sig figs, so I'm going to round this off to 2 sig figs. And we're done. I hope that this treatment allows you to go back and look at this type of problem maybe once or twice again and see what's happening. I want to stress what's going on in the vertical and what's going on in the horizontal direction have to be treated separately, because the equations and variables of the vertical domain involve acceleration, but the horizontal direction does not have any acceleration due to gravity in it. And that the only thing that's common between the 2 domains is time. Thanks for watching. We'll see you in class.